Good morning, everyone, and welcome back to Fundamentals of Engineering with Farhad. We want to solve a structural engineering exam sample question in finding the deflection function in a beam. So, in our example, we have like a beam handling a distributed load of W. One end is a roller and the other is a sliding support at A and ruler at B. And we want to find the deflection function or delta or y for such beam and such loading. So we call the deflected shape, the function for that is called the deflection function delta or y. So this is our multiple choice answers, and let's have a very quick look for the correct answer. So at x equal to L, we don't have any upward and downward because this is there is a support here. So delta is equal to 0. Let's jump to the question. The only one which is not acceptable if you go with this term, that's 6L to the 4 minus 3L to the 4th, and that's not 0. So choice B is already removed from the correct answers. And for the other answers, if you replace X by L, all of them are equal to 0. So we have to solve the problem. The only the only answer is removed is answer B. So this beam is determinate, so we can jot down the summation of moment about B goes 0, and it just says MA plus WL squared over 2 is equal to 0, and it just gives us MA is equal to a clockwise. That's why negative is contradicting the counterclockwise positive arbitrary direction, and it just gives us a MA is a negative WL squared over 2, and that's the clockwise moment at A. So as soon as we have moment at A, we will cut the beam through the length of X and jot down the moment equation, this time for the length of X. We already know what MA is. This time summation of moment in X about X goes 0, and that's mx plus wx x squared over 2 minus half of wl squared. And this is like coming from the moments m at A over here, and this part comes from the distributed function over the length of X. So in such case, we can calculate mx, which is this equation. Mhm. And we do know that y double prime is m over ei. So if we integrate it once, it just gives us theta, and then integrate it once more, it just gives us the delta function. So y prime is integration of m over ei. Take the constant out before the integration and then integrate it. It just gives us theta or y prime is equal to w over 2ei in parentheses L squared times x minus x cubed over 3 plus c1. That's by any integration you will add a constant to your calculation. So now let's go to the boundary condition for our theta or y prime. At x equal to 0, there is no theta. As you can see here at the sliding support, it's like fixed, and there is no also theta. So in that sense, C1 is equal to 0. So y prime function is simply W over 2ei times L squared x minus 1/3 of x cubed. And as soon as we have that, we can move on and calculate the y function based of theta, which is the integration of theta is y, and by doing so, our delta function is this term plus c2. Again, move to another boundary condition for our y function at x equal L, y is equal to 0. At the end of the beam, there is no delta. So in that sense, C2 is equal to a negative 5 L to the fourth over 12. And if that's the case, we can easily get the function of y as the function you can see here, a parametric function for delta or deflection function. So now let's jump to our multiple choices. So we already know the choice B is removed and our y function is this function. If you just rearrange it, you can easily see the correct answer is choice C. Thank you. We'll solve more problems in beams relation. See you in next videos.